Alright, hey guys, what's going on? So today we're going to be talking about transformations of tensors. Again, if you like this kind of content, make sure to hit that like and subscribe button. If you want exclusive content from this channel, make sure to go onto my Patreon page, which is linked in the video, and more content will be coming out there as well. Without further ado, let's get into tensor transformations. So we are now going to talk about how transformations of objects sort of define what they are. We're going to start by considering a vector. Vectors transform as a matrix. So you've probably seen this before if you've seen linear algebra. If we want to transform a matrix, or if we want to transform a vector, we use a matrix, right? And a matrix has elements in it. And the dimension of the matrix is, so the dimension of the vector corresponds to how many rows and columns are in that matrix, okay? And the way you do this is you multiply one row by the vector, multiply the next row by the vector, next row by the vector, and what you get is your shifted or your new values of for the vector components. Okay, and so if we compactify this notation, we say that A prime mu is equal to this matrix, lambda mu nu times A nu, okay? And you can already see here that what we want here is we want the subscript and the superscript of these two guys to match, and then we want the superscript and the superscript to match here. So it's almost like you're canceling things out, but you're not really canceling things out. The idea here is that this sort of helps us keep track of the indices, but it's also going to be very important later on when we start defining covariant and contravariant objects, or contravariant vectors, covectors, if you will. But anyways, I will not undo those circles, and we're going to call this a covariant transformation, okay? And we'll see why in a bit, okay? So now we're going to consider something called a covector, okay? We talked about this a little bit before, but let's go into it a little bit more. So if covectors map tensors to numbers, then the way we're going to do this is we're going to see, here's our covector. So our covector is with mu in the bottom. I sort of like to think of it as co below, right? So the mu here is going to be the subscript, and then the contravariant vector, or just the vector, is going to be in this entry, right? So we have two entries, and we want to take the inner product of the two. And the way we do that is we say, well, when we also want to transform these, well, the transformed version of this looks like this, okay? We're not going to quite transform this yet because we want to see what the transformation of this is like. So we could take these guys out, right? Because this is a vector, this is a transformation of that vector. That's just this right here, and this right here is right here, okay? And then we have this. So what's left over is the E mu, E nu in this inner product, if you will. And we said that this is equal to delta mu nu, right? Because we sort of defined this before. We defined that these are two orthogonal bases, right? So one's a covector, the other one is one's a covector, the other one's just a vector, but they're basis vectors, and we define the basis vector relationship in this mapping to be delta mu nu. So we defined this before. What we're left with is this, and in order for this, in order for this to be this right here, So in order for the inner product here to be equal to the objects just multiplied together, then A must transform as the inverse of A mu. And we can see that because we're transforming, we have this guy right here. If we want to sort of cancel out the effect of this matrix, we need the inverse of that matrix. And so if we have the inverse of that matrix, we would get something that looks like this. So nu, and then, right, so this guy right here is this guy. So we need this right here to be the transformation rule for this guy. Okay. And when we make this transformation rule for this guy, that means that a covector transforms in that way. So that's the matrix that is used in order to transform covectors. Okay. So this is going to be called the covariant transformation. So we still haven't really put a lot of physics to this yet. This is primarily a mathematics playlist, but I like to sort of explain this in ways that are relevant to physics as well, because tensor calculus, if we're being totally honest with ourselves, tensor calculus is very, very important in physics. And we're going to see now what the fundamental difference is between covectors and vectors, or covariant objects, which are covectors, and contravariant objects, which are vectors. So contravariant objects transform against the change of the basis. So let's take an example. Force. Force equals ma. A equals meters per second squared. Super simple. So let's see what happens when we demote meters to centimeters. Well, if we go from 1 meter per second squared, suppose m is just 1, and the force we're feeling is just a unit of 1, okay? We're feeling 1 unit of force. So we go from 1 meter to 1 meter per second squared. If we demote this to centimeters, right, nothing changes here. We're just changing the way we measure things. We increase this value to 100 centimeters per second squared. If we want these two things to be equal, right? If we want these two things to be equal, then that means this has to read 100 centimeters per second squared. Okay, well, clearly there was an increase from 1 to 100, but we decreased from meters to centimeters. So that means, so the force itself increased. But it didn't really increase, right? The magnitude of the force didn't increase. The value that we have, the value that we measure for the force, increases. Okay. But the magnitude doesn't really. They're the same, right? But the value is different. The numerical value is different, and that increases when we go from meters to centimeters. From meters to centimeters, we're decreasing our unit we're decreasing the change of basis, or that change of basis is a decrease from meters to centimeters. Okay, so there's a decrease in the basis, and there is an increase in the force. Well, not really an increase. Again, saying that there's an increase in the force is a little bit of a misleader. We go from 1 meter per second squared to 100 centimeters per second squared. So there's an increase in that value, not in the actual force you feel, though, right? So the component changes, if you will. Okay. So now let's take a look at an example of a covariant object. Well, okay, how about the electric field? The electric field is volts per unit distance, voltage per unit distance. So again, let's go from meters to centimeters. Well, for 1 meter, there's 10 centimeters. What happens here? We're dividing by a bigger number. When we're dividing by a bigger number, the component is decreasing. Okay, so the component decreasing in numerical value. So when we demote from meters to centimeters, we're also demoting from our electric field value from volts divided by 1 to volts divided by 10. So these two things are decreasing. So these are two fundamentally different objects. In one case, we have something that's increasing as we do that demotion from meters to centimeters. And in the other case, we are seeing something that's increasing when we're doing that demotion or decreasing, right? So I might have said that backwards, right? So this thing is increasing when we do that demotion, and this thing is decreasing when we do that demotion. And these are two fundamentally different objects, and what's super interesting here is that there's an equation that relates the electric field to the force, right? And the electric field E equals, I believe it was Q divided by force. I think they're inversely related to one another. This doesn't really matter that much. The point is that Q is charge, and it's just a number. So one object, the covector, the other object, the vector, are being applied to one another to give us a single number. And so, in the world of physics, we can see this is indeed the case. And in the world of mathematics, we can also see now that this is indeed the case. Okay? So, to sum up, our contravariant transformation looks like this. This is against the basis transformation. And our covariant transformation looks like this. This is with the basis transformation. So now let's talk about tensors. How do tensors transform under a change of basis? Well, suppose we have this object here. Right? So this object here is a tensor. And this tensor, we can say that this is equal to when we change the basis, right? So we could change the alpha base, the E alpha basis. Right? So here's our alpha, and this is a vector, right? So this is a basis vector, not a basis covector. This here is a basis covector. This is a basis vector. So the transformation for that rule, or for that, is right here. So that's this guy right here. For this one right here, that's this right here, right? So here's our beta and our beta. Here are, and we're summing over these two, these indices here. Can't remember what the name of, I think these are Greek letters, but we're summing over those. And then in the covariant basis vector case, we are summing in this direction, right? We're summing row over row, and here's our gamma. All right, so we could take these are all the matrices. We put them all in front. So here's that transformation rule and here's the basis. So the basis, we can take off the basis now, right? Because in a lot of textbooks, you don't see the basis written down. You always sort of assume that when you see something like this, that all of us, you sort of assume that there is this E alpha, E beta, E gamma there already. But we're not going to make that assumption here. We want to sort of see how this all works. Anyways, here's that transformation rule. And we're just taking out the basis vectors because we just want to look at how the components change. And the components change like this, right? So we have three matrices as opposed to just one matrix. This is the covariant transformation matrix. This is the contravariant transformation matrix. Here we have a combination of contravariant and covariant transformation bases. So this isn't contravariant, or this isn't strictly a contravariant or covariant transformation. This is a very specific transformation under the change of some basis. And so this is what makes tensors so unique and so interesting, is that when you change the basis, say you go from centimeters to meters, or you go from meters to kilometers, or you're changing the basis in some way. If you're considering an object like a tensor in that kind of case, then you can't think of it as something that is increasing or decreasing its value during that change in basis. It's something that's doing something weird with its components under that change of basis. It might be squeezing it a little bit, but then expanding it some. You don't really know exactly what this transformation looks like. All we can say is that it's very specific for a specific type of change of for a change of basis. And so that's what, again, this is what's going to help us understand why tensors are so important in helping us understand what invariant quantities are like under these types of change of bases. But anyways, we want to sum up now with just considering how exactly we define mathematical objects. We define them by how they transform. So a vector transforms contravariantly, right? So that's this right here. A scalar transforms just as a scalar. You change some basis, that number doesn't change. Heat, for example. All right, so the heat at this point in space, if I expand my basis in some way, that value stays the same. Right? That the value of 36 degrees or whatever stays the same no matter how much I stretch or squeeze my basis vectors. It doesn't change. So the scalars do not change under a change of basis. Vectors change in this way. Covectors change in this way, which is what we've seen. And tensors change in this way. Right? So we've seen this too. And this is only specific for a rank. What is this? This is a rank 1-2 tensor. So this is a 1-2 tensor change of basis, or a 1-2 tensor transformation. 1-2 rank tensor transformation. If you wanted to understand how, say, a rank 4-5 tensor transforms, that's going to be completely different. Okay? And it's going to have its own unique transformation. Here, this is just an example. So tensors are very unique. They're very specific to, depending on the rank of the tensor again, it transforms in a very, very unique way. Now, we can put some more physics to this. So when we're talking scalars, a good example of this would be temperature, right? So temperature, you have some temperature field, and the temperature field, it really doesn't change. This whole room that I'm in right now, no matter how much, if I measure the volume of this room in centimeters or meters, the temperature at each point in this room doesn't change. So something physical, something physics related would be temperature. For a vector field, we can all think of some vector field, right? We can have a force vector, a vector force field. We can have a force vector field. We can have a flow of some object being described by a vector. So flow. For covectors, again, I just gave an example, the electric field, right? So I'll just put electric field for right now. Electric field. And so this electric field, this electric field we saw transforms as a covector. Electric field, there's a covector at each point in space, and those covectors are defined by how they transform, which is in this way. So that's an electric field. And then tensors, in tensors, the case of tensors, we see things like g mu nu, right? So g mu nu, this is the metric tensor. So I will just put this in words, the metric tensor. We will also see the Riemann tensor. We also will see the Weil tensor, and so forth. There's so many different types of tensors out there. They tell us a little bit about how, and these tensors are really applied to GR. and they help us understand GR, which is, we'll go through that in another playlist. But this is how these, so what I have here now is a summary of the name of the object, how they transform, and some examples that we will see in the near future. But with that being said, I hope you guys like this kind of content. And if you do, please hit that like and subscribe button. Go onto my Patreon page if you want some exclusive content where more stuff will be posted. And with that being said, I will see you guys in the next video.